We're live.
All right, hello everyone. Thank you for joining us for our live session. I'll go ahead and hand this over to Chris and we'll start taking questions.
Okay, thanks, Matthew and Alexander, and everyone. Welcome. I'm coming to you today from Florence, Italy, where I've moved from London, where I was on sabbatical. This is the last little leg of my sabbatical. Be back in Tucson 2 weeks today, actually, for our next live session back home. Out of the frying pan into the fire. It's actually very hot here. It's about 40 degrees. We have to use Celsius here. In Tucson, probably a bit hotter. The floor is open for your questions.
Okay, the very first question is from Richard Elkins, who is on with us live, who asks, regarding the grand track theory of Jupiter migration, when we find an exo-Jupiter or giant planet close to a star, is this evidence for the absence of a neighboring large planet in the same system?
So I'll back up to say what the question is referring to. As the first exoplanet discoveries came in the mid to late 1990s, there were a preponderance of what are called hot Jupiters. There were Jupiter mass planets or similar to Jupiter mass planets that were on far hotter, tighter, quicker orbits than Jupiter is in our solar system. Jupiter is 5 astronomical units, 12-year orbit. So these were Jupiters that were a couple of months orbits, maybe even down to a couple of weeks, and situated much closer than Mercury is to the sun. So the question is, how did that happen? The grand track theory was a theory that evolved, that emerged after a decade or so of theorists and observers talking about these discoveries. It was mostly put in place at a very famous or influential exoplanet meeting in Marseille in France. So it's sort of, the grand track theory is tied to Marseille, and a research group there was very instrumental in disseminating it. And it's basically the idea based on simulations. It's sort of illuminating our understanding using simulations of how planetary systems evolve, that shows a mechanism by which Jupiters form quite quickly, quite far out in a solar system where our giant planets are, because that's the only place where there's enough material. And then they migrate inwards once most of the gas and debris has been cleared out or sucked into planets, and then park in a orbit where they're tidally locked, and then sometimes fall into the star. So the grand track theory also deals with what happens if you have more than one massive planet. And it's true that when there are multiple giant planets, the ability of those planets to migrate is affected, because they can set up resonance situations where the multiple giant planets are sort of locked into a resonance which stops them from migrating, and so they don't end up in the classic hot Jupiter state. And basically, there are a lot of options. This is not a single scenario. The grand track theory is a theory that describes how giant planets form and then generally migrate. But how they migrate and what happens when there are multiple giant planets is actually very complicated, and each situation is almost unique. And really, not all these scenarios are completely understood, because the missing piece of information, of course, for exoplanets is we don't always know when they form. We don't know the age of these planets, and we don't know what the initial conditions of those young star systems were. So it's a sort of working hypothesis, if you like. Ready for the next question?
Thanks, Chris. The next question is from Rachit Patil, who's on with us live, who asks, is it true that underground nuclear explosions or non-nuclear explosions have similar structure to meteor impacts, and can we study them to understand more about meteor impacts?
There are some similarities, definitely. Underground nuclear explosions are not very far below the surface. Obviously, a meteor impact is at the surface and sends shock waves through the crust, and those shock waves, penetrate large distances. In fact, the seismic waves from a large meteor impact will travel entirely through the Earth and be registered by sensitive seismometers on the far side of the Earth. Same is true of a nuclear explosion. So yes, there are similarities, because underground nuclear explosions are still very close to the surface and still in the top crust layer. So the way they impact the crust and send an impulse through the rock, and the way that those seismic waves refract through the Earth's mantle is very similar. And so I think there has been illumination from nuclear explosions. Of course, some of the meteoric impacts on the Earth historically exceed any nuclear explosion. For instance, the KT impact, the impact 65 million years ago that we think played a role in extinguishing a large fraction of creatures on the Earth, including dinosaurs, that equivalent nuclear power, if it were an explosion, exceed the sum of all the world's arsenals by a significant factor. So meteor impacts far exceed any nuclear explosions. But you can extrapolate what we learned from nuclear explosions to understand meteor impacts. Ready for the next question?
All right, the next question is from Brian Perry, who sent us a question via email, who asks, I've seen a lot about new discoveries in the news. However, one issue that I haven't seen is how are astronomers responding to the telescope controversy on Mauna Kea? I realize it's likely a hot-button topic, but wonder what insights or resolutions you see may be possible in that conflict.
Yeah, it's a good question because it has very much been in the news, but it's been in and out of the news actually for years. And I'll have to declare my sort of partisan bias. I hope I don't display the bias in my answer. The TMT, the 30-meter telescope, is a collaborative project between Caltech and the University of California. Since they were the initial proposers, since expanded to include a number of countries as well, so international collaboration. University of Arizona, my university, and the mirrors we make in our mirror lab are part of the Giant Magellan Telescope, which is a slightly smaller 22-meter equivalent aperture telescope that will be in Chile. So these are sort of competing projects. And the third competing project is the extremely large telescope, the ELT of the European Southern Observatory, also to be located in Chile. So these are the three huge optical telescopes for the next few decades. The TMT had a pretty strong start based on the mosaic hexagonal mirrors technology that's used in the Keck telescopes, just scaling that up basically. And so they had a good head start and a well-tested technology, and they also had a site identified on Mauna Kea. Mauna Kea is pretty full, actually. There are more than 24 telescopes on there, and half of those are very large telescopes. And so the real estate on the summit is pretty much occupied, but there was an available site. Mauna Kea went through an environmental impact statement, and as over some period of years, not the recent controversies, but going back 5, 6, 7 years, there was a sense from some of the native Hawaiians that there should be a limit to the amount of hardware on Mauna Kea because it is a sacred mountain in their culture. And of course, the islands of Hawaii were Hawaiian long before they were briefly English and then eventually American. There was an agreement reached whereby if any large new telescope was put on Mauna Kea, other telescope would be decommissioned. In other words, to keep the number of very large telescopes constant and not increase it. And that's pretty much consistent with the fact that there's not really room for any more anyway. So that agreement was reached, not without controversy itself, but it seemed to be a stable situation at that point. However, in the last 4 or 5 years, and more recently the last 1 or 2 years, opposition to the TMT, to this very large new telescope on the mountain with a very high profile, very prominent, you could see it, of course, from sea level and from far away, has grown. And the basis is the same. It's a sense that this is a sacred mountain that's being sullied, if you like, by such a presence. And then that's been exacerbated by probably, I think even to people in the project, a sense that there was a little high-handedness in the way the international collaboration and even the Hawaiian host, the University of Hawaii, sort of handled the preparation for this telescope, not taking the opposition very seriously, just thinking that it was a small number of people, that these were concerns that should be outweighed by the fact that these telescopes were going to bring jobs to Hawaii and to native Hawaiians and so on, so people should appreciate the economic benefits. So I think that was a little arrogant and a little high-handed, and of course it backfired because the opposition has grown. And the legal aspects have moved through various stages of injunctions and then changes to those injunctions and new environmental impact statements that were requested or required by the courts, and then the execution of those statements. So the project was stalled, the TMT project was stalled for a couple of years. was recently given the green light, the go-ahead, was supported by the governor of Hawaii and the state of Hawaii, and the legal obstacles were cleared for construction. But a new set of demonstrations emerged, and they've grown over the past month or so, as people can see if they just look at the news, to a large number of Native Hawaiians and their friends and allies who are really trying to stop this construction. And I think it's just too early to say what's going to happen. This is a $1 billion project, and you could just be very blunt and say, well, it's just a few dozen or 100 protesters and a $1 billion project that's going to bring lots and lots of jobs to Hawaii, so they should just be quiet and go away. But that's not a good way to look at it, and that would just exacerbate the problem. And it doesn't really seem like there's a good dialogue happening right now. So I think at the moment it's a pretty unhealthy situation, not just because there's a lot of sort of anger in the Native Hawaiian community, and there are these kind of active demonstrations where the governor of Hawaii is potentially calling in the National Guard to clear people away. So that's a significant confrontation. It just doesn't seem like they're talking at the moment. So I watch it, as do other people. And astronomers are, of course, concerned. They want their big telescopes to be built. But I would probably say, among most of my colleagues, the ones that I talk to, even the ones who have skin in the game, in that they're working at institutions that will build this one telescope, they don't want it at any cost. And so I think, hopefully everyone will sort of cool down and calm down, and there'll be some dialogue and maybe some resolution of these issues. Thanks for that question. I'm ready for the next one.
Thanks, Chris. The next one is from Junaid Atta, who asks, what is the nature of the Higgs boson, and what kind of charge or other properties does the Higgs boson contain?
So the Higgs boson is in the simplest terms, is the last missing piece of what's called the standard model of particle physics. The standard model of particle physics is a highly successful theoretical construct to explain all subatomic particles. And those particles are grouped into broad categories, which are fermions, or half-spin particles, and bosons, which are whole number spin particles, where the spin is not a spin like a spinning top or a spinning planet. It's a quantum property. So you should not be literalized as a spin. And so there are various subatomic particles in various families with various masses, and there are 4 fundamental forces. And that entire package is the standard model. What was missing in the standard model was any mechanism to explain why the particles have different masses. Why, for example, are protons and neutrons 2,000 times more massive than electrons? Why are there muons that are 10 times less massive than a proton, or a few hundred times more massive than an electron? The masses of particles seem completely arbitrary, even though they fit into these different families. And so the Higgs mechanism, as it was originally proposed in the 1960s, it's named after Peter Higgs from the university where I got my PhD, University of Edinburgh. Peter Higgs proposed a mechanism that would give all particles their mass, and essentially everything in the universe its mass. And it's best to think of it rather than as a particle or a boson, which would be a integer spin particle, thinking of it as a field, that is a sort of ambient potentiality that exists through space. You could almost think of it as a viscous fluid, an invisible fluid, where the mass of particles represents their drag, or through this viscous fluid, only it's not really a fluid, it's just a field. And so that becomes a way of sort of visualizing roughly how something that's ambient in the vacuum of space, that's a field, could imbue particles with mass. And the larger the inertia of the particle, the larger its mass. So it's a mechanism for explaining mass. It doesn't, in and of itself, however, explain why the particles have the very particular masses they have. So it's not worth overstating the importance of the Higgs mechanism or the Higgs boson. It doesn't explain everything about fundamental particles, but it does provide an important mechanism for why they have mass at all, or in the first place. So it was very important. It was detected in CERN over a period of 3 years, from 2011 to 2013, as a resonance at about 130 GeV, giga electron volts. That's the equivalent mass of this field, if you like, or this boson. And its discovery led within a couple of years to the award of the Nobel Prize because of a very major discovery. So it was a really dramatic occurrence in high energy physics. It was a stunning success for the Large Hadron Collider, of course. And since then, things have actually been pretty quiet. So since discovering the Higgs, the Large Hadron Collider hasn't had any amazing successes of that order. And as I said, the Higgs mechanism and boson doesn't solve all the mysteries of particle physics. Ready for the next question?
All right, thank you, Chris. The next question is from Tanya Davis, who asks, do you know any new information about the American Space Force and if it has plans to include asteroid defense in their mission?
Right. The American Space Force, people will recall, is a proposal of the current administration, particularly been talked about by Vice President Mike Pence, to have a new branch of the armed services. So essentially to create a new fifth branch of the armed services to do space operations, or a space force, as it sounds like. So this is independent of NASA. NASA's a civilian space agency. It's been around since 1959. This Space Force would be a military agency, and so the activities of the Space Force would include, obviously, a number of things that would be classified or secret that the public might not learn about. And that fact alone has made some people nervous about it, because NASA is a civilian space agency. Occasionally they've taken military payloads, of course, on the space shuttle and in their various rockets, but fundamentally it's a civilian agency with open books and budgets that Congress sees and the public can see. The Space Force would not be in that category. Parts of its budget, as with the Pentagon, would be not visible to people, as would some of its projects and missions. It was imagined at the start that it wouldn't be purely military, that it would do some civilian space work, and asteroid defense would be one natural part of its mission. And so to answer the question, yes, the Space Force was proposed with asteroid defense, or protecting the Earth from large Earth-crossing asteroids that might hit the Earth, so monitoring for their existence, tracking their orbits, and in the very unlikely eventuality that one is headed for the Earth, actually dealing with them by deflecting them. That was part of the Space Force's purview. But the Space Force is vaporware at the moment. It has not been brought into existence by an act of Congress. The administration can propose, but it actually would have to be created by Congress as a new branch of the armed forces, and that hasn't happened. So the Space Force at the moment doesn't exist. Ready for the next question?
The next question is from Mariana Hilowele, who asks, why are Saturn's rings linearly arranged? I know there's depths and heights to them, but I never understood why they don't make a globular structure around it.
So it's a good question, and Saturn's rings and the rings of all the giant planets, remember all the 4 giant planets in the solar system have ring systems. Saturn's just happens to be the most prominent, so obviously so prominent that it was discovered as soon as we had a telescope 400 years ago. But the other 4 planets also have ring systems. And those ring systems form in a sort of directly analogous way to the formation of the planets around the sun. So the initial gas cloud that formed the sun was rotating, and the preferential collapse of a roughly spherical gas cloud will be preferentially along the poles of its rotation axis. And so a sphere turns into a disk, and the central object getting most of the mass becomes the sun, and what's left around it is a lot of particles. Those particles eventually sweep into planets. But before they sweep into planets, the early solar system would have some resemblance to Saturn's rings on a very large scale. Well, Saturn's rings is the same situation. The object that formed Saturn was a gas cloud within the proto-solar system nebula, and it collapsed preferentially along its poles because Saturn is spinning, and the particles collapse into a disk or a plane, and those particles continue to orbit around the planet. Now, in the case of Saturn, there are, of course, moons of Saturn. Many of those are beyond the rings. The rings are sort of leftover debris that was not sufficient to form moons. There are little moonlets that orbit within the rings and sometimes clear out gaps in the rings. But the rings particles are essentially failed moons. And they are very thin because the vertical force that leads them to collapse by gravity and the fact that the particles don't collide that often means that they settle into a very thin planar structure. And the rings of Saturn are incredibly thin. They're about 100 meters thick. And remember, they're about 1,000,000 kilometers across, side to side. So that's fantastically thin, as thin as a sort of sheet of paper compared to its size. And they stay in those orbits, and those orbits don't really change. Eventually, over a long time, if you make simulations, Saturn's rings will dissipate and go away, and that seems to have happened with some of the other giant planets. So they're not permanent features of any planet. Ready for the next question.
Thank you, Chris. The next question is from Kathy and Art, who asks if you could discuss the relative importance of things like quantum tunneling, pressure, and temperature with regards to fusion in stars.
So quantum tunneling is actually a core piece of physics in understanding how stars work. And we can just talk about the sun. It's how the sun works too. If you do a simple calculation in the center of a star where the temperature and the pressure is very high, you can calculate the energy or the speed at which protons are colliding in the center of a star. And it's a plasma, so the electrons are there mixed with the protons, but the protons are where the mass is, and the protons resist coming close together because of their electrical force. If you do a standard classical calculation of inverse square law of electrical repulsion, then obviously as the protons get closer together, the repulsive force goes up. And if you do the simple classical calculation, the protons would actually never fuse. They would not have enough energy to fuse in significant numbers. It would happen, but not very much. It's only the quantum tunneling aspect, so including quantum mechanics in the calculation, that gives you the right answer. And that basically means that the particles, protons, are not really hard-edged particles like BBs or billiard balls or whatever. When two protons come close together with very high energy, there's a finite chance that they actually overlap each other or merge with each other, and that's the quantum tunneling effect. And that increases the probability that fusion will occur between any two charged particles. And that boost in probability from the quantum tunneling effect is entirely needed to explain stellar fusion or the fusion of the sun. You simply don't get the right reaction rate, you don't get the right energy out, and you don't explain sunshine. So quantum tunneling is actually a really essential part of understanding stellar physics. Ready for the next question?
Our next question comes from Styles Hoot Owl, who asks, what are your thoughts about the recent theories based on dark stars and their probable connection with supermassive black holes?
So dark stars, I mean, there are ideas that there are, of course, massive stars that may not formally fit the definition of a black hole, but they're dark because either because they're not substellar, because their energy rate is too low for them to be visible, or because indeed they've turned into a situation that represents a supermassive black hole or a massive black hole. Dark star was, in fact, the original term for black holes over 200 years ago. So if we take dark star as just meaning a star whose gravity is such that light cannot escape, then formally you are making the definition of a black hole. And those objects sit at the center of galaxies as well as places where stars have died. In the center of galaxies, they're much bigger than individual stars. They can be millions or billions of times the mass of a star. And so they represent the merger or coalescence of a lot of smaller black holes, or a black hole that's grown by accretion, by chewing up stars and swallowing stars whole in gas over billions of years, and it's steadily grown. So a dark star is really just a colloquial term for a massive black hole that forms and grows at the center of a galaxy. Ready for the next question?
The next question comes from Hernan Reyes, who has taken our astrobiology course and is following along with us, and he asks, why is it that NASA and the European Space Agency aren't concentrating more efforts on looking for life in the solar system, for example, on Europa with a joint mission? Why are we spending more time on Mars than trying to answer this critical question about whether life can emerge elsewhere in the solar system.
And it's a good question, and planetary scientists whose business this is have the same question. There are many experts on Mars who are quite happy with all the attention on Mars, but there are some of my colleagues and people I've known for a long time who find the outer solar system extremely exciting. Europa, of course, Titan, of course, Enceladus, where we know there are the three ingredients for life, and probably another half dozen places in the outer solar system where the potential for biology exists. The simple answer is that outer solar system missions are much more expensive, they're much harder, and they take much longer than a mission to Mars. It's as simple as that. Mars is a lot closer. The time scale for developing a Mars mission is maybe 5, 6, 7 years. Outer solar system missions, 10, 15, 20 years. These are obstacles to a space agency, either one, NASA or the European Space Agency, whose budgets are set every couple of years and have a real trouble with long-term planning. So there's a Europa Clipper mission, and it's quite an exciting mission. But of course, it's a slightly timid mission that is going to do an extensive inspection of Europa by orbiting it, which hasn't been done since the 1970s, so it will still learn a lot. And there's an idea to splash down a projectile and sniff the material that gets sent up to see what it's made of and do spectroscopy. But there's not going to be a lander. There's not going to be a machine that could melt through the ice and explore the European Ocean. And that's really what people are waiting for. Recently, you probably noticed there was a very avant-garde and exciting proposal for a Titan mission. It got a NASA start, it got a sort of $500 million start. And that's very exciting because that's a NASA mission that's going to use sort of, ultralight airplane technology, which is fairly new, to fly around on Titan and sample the Titan oceans, mostly made of ethane and methane, which could be living. It's going to take a decade again to get there, but it's been funded. So that's an exciting new development. But generally, Mars is going to always get the bulk of the attention because it's just easier and quicker and cheaper to develop missions for Mars. Ready for the next question?
Sorry, the next question comes from Jana or Yana Limirusu, who asks, how does space weather interact with Earth's weather? Sorry.
Space weather has an impact with the Earth's weather because the Earth has a magnetic field. So space weather mostly originates from the sun, and it's based on cosmic rays. Well, they're cosmic rays which come from beyond the sun, from beyond the solar system. So they're high energy particles, surging around and through the galaxy, and some of those impact the Earth too, cosmic rays. But the bulk of space weather is originating from the sun, a huge source of energy and high energy particles fairly close to the Earth. The interaction between those incoming particles and the Earth is governed very much by the Earth's magnetic field, which steers the charged particles along magnetic pole lines and actually funnels them typically to the magnetic poles of the Earth, and in a sense deflects them from the main parts of the Earth, the mid-latitudes of the Earth. But many of them, of course, get through. It's not a perfect process. And these charged particles and high-energy radiations can have serious impact on our telecommunications. They also, of course, are highly energetic particles that, when they're surging, they increase mutation rates. They can increase the rate of skin cancer of people who are outside when such radiation is around. So they have significant impact on our life and our planet. The flares of the sun and the super flares that only happen maybe every 100 or few hundred or 1,000 years, those are extremely damaging space weather events, and there doesn't happen to have been one for decades. But if there were one, it would have some quite dramatic effects on our modern electronic infrastructure. So space weather is a serious thing that astronomers try to understand, and that federal agencies and governments actually have to try and manage because of the impacts on our infrastructure when it gets out of hand. Ready for the next question?
All right, our next question comes from Wolf and Bree, who's on with us live. who asks, if you could send a lander, rover, or satellite to anywhere in the galaxy, where would you send it and why?
Anywhere in the galaxy. Okay, so that's a big open space. We've already dealt with the solar system in a different question, but if we're talking about beyond the solar system, then I would say Proxima Centauri. We very likely have at least one Earth-like planet in our nearest star system, four and a bit light years away. And in terms of a plausible mission, because we do have the miniaturization of nanobots and the propulsion technology in principle, or acceleration through solar sails to get there in a reasonable time. Breakthrough Starshot is the current commercial idea to do that. That's the place I'd go, because that's essentially the nearest Earth-like planet, the nearest place we might find life 2.0. And to be able to go there with an actual probe as opposed to just inspect it with telescopes would be incredibly exciting. So that would be my choice. Ready for the next question.
All right, our next question is from Blue, who's on with us live, who asks, why do we only see one side of the moon?
We see one side of the moon because the moon is, relative to the Earth, a very large satellite. And when a satellite is large compared to the planet it orbits, the tidal interaction between the two is strong. Tidal force is essentially the difference in the gravity between two objects, between the near and the far side of the object. And when the objects are large and the distance between them relatively small, the tidal force is large. And that tidal force essentially means that the large object, the planet, reaches out and sort of grabs the moon and stops it from taking its normal spin and becomes tidally locked. And so tidal locking is essentially the result anytime you have a large moon orbiting a planet or very close to it. And we see a number of situations like that. Mercury, of course, is tidally locked to the sun because it's very close to the sun and it's a fairly small planet. So the moon has been tidally locked to the Earth for really since its formation. That will not always be the case, however. There's a slow process happening where the moon is getting further from the Earth by about 4 centimeters a year. It's measured by the reflectors left behind by Apollo. And as the moon recedes from the Earth, which is basically just due to a transfer of angular momentum, energy and angular momentum being conserved, the moon is losing rotational energy, gaining angular momentum, and moving further from the Earth. Eventually, it will actually not be tidally locked anymore once it's moved far enough away from the Earth. And I suppose eventually, if the solar system lasts that long, the moon may not even be bound to the Earth. It may be liberated into the solar system. Ready for the next question?
Thank you, Chris. Our next question comes from email from Gitanjali Rajulal, who asks, in all the explorations for life on other planets, astronomers are always searching for liquid water. But why should liquid water be a prerequisite for life? Why can't there be life forms that survive without liquid water, or water in any form for that matter?
Right. It's a good question. And it's a completely reasonable question. Why should liquid water be a premise? The simple answer is it's just very pragmatic to start with a position that life elsewhere that we don't even know if it exists at the moment. So we have to be a little conservative in how we look for it. We don't know how to look for strange life. That's part of the answer. And the other part of the answer is, if we look at the only form of life we know, which is the wide range of life forms on the Earth, every single one of them uses and needs and depends on water. And so water is an essential ingredient for every aspect of life on Earth. Now that's obvious since a lot of life is in the oceans, and humans and mammals are 2/3 or half water at least. Even the driest bug or beetle is about 20% water. So even land creatures are a significant fraction of water. But if you talk about the driest forms of life you can imagine, life in the Atacama Desert, lithospheric life, microbes within rocks, they still need water to live. Now their metabolic rates may go very low, their cell division rates may drop dramatically, but they still use water to live. And so that's a very strong indication from the diversity of life on Earth in its entire history that water was essential to life on the Earth. So that's the strongest reason why it's become a premise of looking for life. because every form of life we can see or discover on the Earth uses water. But the question is well posed, because clearly that doesn't mean that every form of biology in the universe needs water. It's likely that life will need a solvent of some kind, a liquid, but there are other liquids that could suffice. Cleaning fluid, methane. There are various that is methane under pressure, so that it's a liquid. So there are various liquids that are inert enough and facilitate chemical reactions that could potentially serve as a medium for biology of some strange form. Probably the most exotic example near us is Titan. Titan has legs made of ethane and methane, liquefied because of the cold and the pressure, with a small amount of ammonia and water mixed in. And astronomers and biologists have speculated that that very strange chemical brew could potentially host a very unusual and novel form of life. And so that's a place we could actually look for strange life right near the Earth. And people would love to do that experiment. And we're starting to do those experiments now. But basically, yes, life could be very strange. The problem then is the one of a scientific experiment. How do you look for life of unknown function and form? And that's a big question. How do you, as a scientist, design an experiment to test for that life when you don't know what it is? Ready for the next question?
Our next question is from Will Suttles, who is on with us live, and asks, does radioactivity have anything to do with the heat in the Earth's interior? And is lava radioactive?
Yes, absolutely. Radioactivity is the reason, basically, that the Earth is a tectonic planet. So the radioactivity of the Earth is entirely natural. Radioactive long decay elements like plutonium and uranium exist in very small quantities in the universe everywhere, a few parts per billion or a few parts per trillion. But they put out sufficient energy in their radioactive decay that in a mass of rock, they will have a significant heating effect. And so any rocky planet will, just because of the relatively small amount of radioactive material within it, will be generating heat. And if in addition that rocky planet is substantial in size, Earth size or bigger, then the pressure and the temperature is such that the rock will be liquid. So you've got a rock that's turned into magma or liquid form. You've got a heat source from radioactivity, which will drive circulating motions, tectonic plates on the surface, these churning convective cells of basically magma. And so the activity of a terrestrial planet really is driven in significant part by radioactivity. Ready for the next question?
Thank you, Chris. The next question is from Naroon Joe, who's on with us live, who asks, is it possible to turn energy into gravity?
An interesting question. Energy obviously depends what form of energy. Gravity is essentially potential energy, so gravity is a form of energy in a sense. Energy, we know, has an equivalent mass. That's an Einstein principle, equals mc squared, going back to his early discoveries. So energy has equivalent mass, and gravity is a form of energy in the sense that it's the potential for something to do work. Energy is essentially the ability of something to do work. So if you have a gravitating object and you have a particle suspended above it and you let the particle go, the particle will accelerate in the gravity field and gain kinetic energy. So you've turned gravitational potential energy into kinetic energy. That's the most obvious and simple way you can turn gravity, if you want to call it that, into energy by some object that interacts with that gravity. As for turning gravity in a more general sense or in a pure sense into energy, that's probably not possible to do. Gravity is the weakest force of the four fundamental forces by some enormous factor. And we've not found any way of sort of harvesting or converting the force that is so weak into energy that we can then use to do something practical. That's a technology or a physics that is not available to us right now. Ready for the next question?
Our next question is from a live viewer, Mariana, who asks, we get oxygen I guess the more general question is, where do we get oxygen on our planet from, and where do we get the water that is on our planet? Where did it form in the first place?
Mm-hmm. So water and oxygen, two very interesting and important ingredients on the Earth, and they're also obviously unusual ingredients. If we look at the planets in the solar system, apart from Europa, which is a moon of Jupiter, we don't see water in significant amounts anywhere else. And we definitely don't see oxygen in significant amounts. Oxygen is a highly reactive gas, and so it will rust or oxidize almost immediately. So the basic answer for oxygen is that the oxygen we breathe, 1 part in 5 of our atmosphere, with most of the rest being the relatively inert gas nitrogen, that oxygen was produced by microbes starting about 3 billion years ago. The first forms of microbial life on Earth, starting almost 4 billion years ago, were what are called methanogens. They were microbes that gained their energy in a metabolic process that involved methane. They were respirating using methane. Oxygenic photosynthesis, the conversion, for such as what plants do when they respire, of taking in carbon dioxide and giving off oxygen, or what microbes do in the same way as a microbial process, that started about 3 billion years ago. And so over a period of time, probably as much as 1 billion years, the oxygen level of the planet gradually ramped up from an extremely low level, initially to a few percent, and then in the second wave, about 1 billion or so years ago, up to the current value that it has now. And it's been pretty much stable for the last 500 million years. So the oxygen we breathe was produced by microbes, by previous generations of microbes. Oxygen-producing microbes still exist, but with the initiation of life on the land and plants, the development of plants, which first emerged about 400 million years ago, most of the oxygen now that's added to the atmosphere comes from plants. So that's the Earth's oxygen. The Earth's water, we think, was deposited on the Earth by incoming objects like comets and asteroids. There were a mixture of rocky material and frozen volatile material because they were coming from cold parts of the solar system. And as they landed on the Earth and impacted, those volatile materials would vaporize or liquefy, and that turned into the Earth's oceans. As a fraction of the Earth's mass, the Earth's oceans are extremely thin. They're thinner than the skin on an apple compared to the size of the apple. So even though the Earth has what seems like a lot of water, it's actually a very small fraction of its mass. Ready for the next question?
Our next question is from Jeff Wolf, who's on with us live, who asks, if dark matter is roughly 5 times normal matter, shouldn't black holes have the same ratio of dark to normal matter, or at least have added large amounts of dark matter, especially supermassive ones?
Right. So that's a good question. What is the relationship or the role of dark matter with respect to black holes? So black holes, especially the kind that are dead stars, were formed from normal matter that just collapsed into a state where nothing could escape, including light. Those normal stars would have included, just as part of their complement of material, some small amount of dark matter. But the key thing to remember is that the dark matter in the universe is mostly distributed on large scales. It's not concentrated gravitationally as much as the normal matter is. And so it's much more diffusely distributed. And so a typical black hole will actually not contain very much dark matter at all. Remember, of course, also that dark matter does not interact through the electromagnetic force. It only has gravity. So if you start with a very small amount of dark matter anyway, which can clump by its own gravity, but that's not very much because its gravity is weak, and it can't interact in any other way with normal matter, then it's sort of like the black holes don't know or care about the dark matter, and the dark matter ignores the black holes. And the same is true with the supermassive black holes. So the simple answer to the question is that black holes of any size contain very small amounts of dark matter, because most of the dark matter in the universe is distributed on much larger scales. Ready for the next question?
The next question is from Will, who asks, is there any danger from the radio waves apparently aimed at us from Sagittarius A star?
No, radio waves luckily are fairly innocuous. They're low energy. Um, and they don't really have any damaging effect. I mean, on the Earth with our cellular communications and radio transmitters, we're sort of dosed with radio waves, with centimeter, millimeter, meter length radio waves all the time. And the ambient radio waves we have around us, especially from our cell phones that we hold close to our heads, dwarfs any radio waves from any cosmic source by many, many, many orders of magnitude. So basically, cosmic sources of radio waves, including Sagittarius A star, the region where the center of our galaxy houses a black hole, are of negligible impact on humans. And they're, of course, barely measurable unless you have a large telescope anyway. Ready for the next question?
The next question is from Satyam, who asks, how is Einstein's relativity actually conflicting with or connected with quantum theory?
At the moment, it doesn't conflict with it, but it's not connected with it. Relativity and quantum theory are in conflict only in the sense that they have fundamentally different bases. And so when you work the phenomenology, work the mathematics or the physical formalism of general relativity, you're working in a tensor theory of gravity where mass and energy distort space and time. And in that self-contained mathematics, you can understand how gravity works and how objects move in the universe. Quantum theory applies on a far different realm. It applies on the microscopic scale of subatomic particles. And in those realms, gravity is a sort of vanishingly weak force. So gravity really doesn't play a part. So I would say, rather than being in conflict, the two theories are just completely different realms of physics, situation, and experience, and strength of forces, if you like. So they just don't speak to each other, basically. To merge them or to mate them or to find a unified theory is therefore very difficult. That's part of the reason why it's so difficult, because their realms of application are so different. And so people have had to reach in trying to unify them to very new ways of thinking about nature. String theory is one of them, and I'm not going to give a long answer here, but basically you have to do something pretty novel with physics to somehow combine these two theories that are so dissimilar from each other. Ready for the next question?
Okay, so we have time for one final question, and then we will wrap up for today. The last question is going to be from Ryan Weber, who asks, do you think that adaptive optics technology will make its way into affordable amateur astronomy gear?
That's an interesting question. I think yes, actually. Adaptive optics is now standard issue equipment on all the world's large telescopes. Essentially, you build your large telescope and you just have a layer of the telescope, sometimes at the secondary mirror, sometimes at the primary, more often for a big telescope at the secondary mirror, where you adaptively, you have a thin mirror that you can flex its shape in response to measuring the wavefronts changing in the atmosphere, usually probed or sensed with a laser. And you feed that information back into your changing shape of your mirror, and you correct for those undulations in the wavefront caused by motions in the atmosphere. That's a standard issue equipment. Now, on a big Earth-based telescope, a 5, 10, 20-meter telescope, those systems are not cheap. Those systems cost tens of millions of dollars minimum. The cheapest system I have ever seen for smaller telescopes where you really can't afford to spend a huge amount of money is maybe $1 or $2 million. Obviously, that's nowhere near the realm of amateur astronomy yet. But I would say some of the fundamental technologies of how to build flexible mirrors and adapt them piezoelectrically are actually quite scalable. And they're not fundamentally state-of-the-art technologies. The piezoelectric actuators, for example, that they use on secondary mirrors for adaptive optics, they're like off-the-shelf components. The computational power required to do adaptive optics is getting cheaper and cheaper. So if I were just to extrapolate, I'm going to guess that in maybe a decade, it will be possible for sort of very high-end amateurs to, off the shelf, it's a small market, so it's not clear how the pricing will work, but off the shelf, get a basic adaptive optics equipment for something like a few tens of thousands of dollars. I don't think it's going to come down much cheaper than that very easily, but that does start to put it in the realm of high-end amateur astronomers or amateur astronomers that form a consortium. So yes, I'll be optimistic and say amateurs will get their hands on adaptive optics, say in a decade. And thanks for that question, a good one to end with, and for your very interesting and varied questions as always. We'll be back with you. We'll pick a slightly different time slot because I'll be back on the Tucson time zone, and we'll be with you 2 weeks today. So thanks for your questions, and thanks to Matthew and the team for helping facilitate this session. So goodbye.